we will do in this lecture is we are gonna discuss one of the algorithms that are used for to sort of like to play with the data, to process the data. Principal component decomposition, or known as PCA. So let's see what is really what we are trying to do here. Typically, you have samples here, okay, samples, and these samples have variables. Well, أعطيني examples. Let's just say, for example, we are sampling restaurants around the area. So what are the variables? Well, let's say one variable, and by the way, the variable can be a feature or attribute. We say so. These are the different words that people use. Let's say we use the one variable is how far this restaurant's how far away it is from the university. Number one, what's the that's one variable or one feature. What's the average cost of the meal in this restaurant? This is another variable. What are the ratings that people are giving to this restaurant? Okay, this is the third variable, etc., etc., etc. So these are variables about. So I go and sample restaurants and how many samples. Let's say, for example, if I have 100 variables or 100 features that I'm reporting per restaurant, and let's say I have 10 restaurants, so therefore this matrix is of the data. I have 100 features for every restaurant, and I have 10 restaurants. But now, of course, this is manageable. Now, suppose I'm sampling restaurants on the let's say, for example, on the basis of 10,000 features, for example. Every restaurant I go and collect all these features for the restaurants. And let's say I'm doing the restaurants on the Middle East area, where I have about, for example, 2,000 or 200,000 or a million restaurants, for example, again. Now, you can see now my data is growing astronomically. You have a large number of restaurants, and at the same time, you are collecting so many features. Now, obviously, these features that I am talking here about are not independent. Yani they correlate to each other. Some features are redundant, and some features are not redundant. So what dimensionality reduction does is it reduces number of features from big N, let's say 10,000 feature, to small n, let's say 10 features. Okay. This analysis, why we do it? Because simply it simplifies things. Plain and simple. It makes things very simple. Instead of dealing with this gigantic data, now I can deal with this smaller data. Okay, so clearly this leads to less computation, less storage. If I deal with the small n here, number of variables. Notice number of restaurants and samples do not change. Okay, what changes is the number of variables here. I shrink those number of variables. So I identifies this process identifies the most significant features. We remove redundancy. Okay, typically good for visualing data. So for example, I can reduce these into just a 3 or 2 features, and then I start doing 2D plus or 3D floods if that is feasible. Okay, so typically, by the way, dimensionality reduction typically used as a pre-processing in other algorithms like clustering algorithms. So it is a very good pre-processing step, because what now they do? They reduce data. That's the magic that we do here. Typically, dimensionality reduction algorithms are split into 2 categories, feature selection category and feature projection category. And feature selection category, basically we select a subset of the features. So let's go back to here to this example. This subset here is sum of, oops, sorry. And the screen disappeared on me. Let's see what happened here. Oh, here we go. This small n here is a subset. We did not change these features. No. They are the same. So I just took subset of them. So this is the feature selection. Now, of course, for these type of, let's see, this is giving me a little bit of hard time. Okay. Okay. All right. So this feature selection, it selects a subset, and typically this feature selection, okay, the results are interpretable. Yani when I select some of the features, I can understand what are these features that are important, the top 100, the top 10 important features or variables, and I can understand them. Now, as opposed to what? Well, as opposed to the other part here, which is other, let's say, for example, let's say category, it is feature projection. So in this case, I don't select, I rather extract the most important features by applying transformation. لاحظ الكيورد يعني كل كلمة هنا is مهم جدا. The transformations means I no more have the original features. I have now new features. So if I go to my diagram here, now this subset is not the same as or some of this. La. These are brand new ones that I create. They kind of extracted. So I cannot sort of like do a one-to-one mapping here. Okay, as we will see in the PCA algorithm. And typically we can have linear and non-linear. And in the linear algorithms, I have the PCA, which is the principal component analysis. I have linear discriminant analysis as well, and singular value decomposition. And I can have non-linear methods, okay, as it shows right here. But in this class, what we'll do, we're going to pick just one algorithm, right, which is the PCA, which is right here. Now, I encourage all of you, from broadening your information perspective, is to check out the other algorithms and read about them. We can't cover all the algorithms in this class. Now, feature projection has an important feature, an important criteria. It produces new but لاحظ uncorrelated features. لأنه one problem of feature selection is that you might end up selecting correlated features. طب شو معنى correlated? Correlated, whenever you hear the word correlated, it implies redundancy. So عندك features that you are selecting features, but they have redundancies among them. Okay? All right. So which really wastes your space and processing time. What you really want is uncorrelated orthogonal features. So this is provided by the feature projection methods that we have here. So that's one key advantage. طبعا typically it is more effective than the other method. Especially in many cases we see features are correlated. So creating a brand new features that are uncorrelated is a key feature for the feature projection method. So now let's talk about PCA. So now we know that this lecture is about what? Dimensionality reduction. And we know that there are multiple methods of dimensionality reduction. Selection, projection. Well, the selection is out scope of this course. We looked at the projection and we say we're going to pick one example, linear algorithm example, and we will explain the PCA. So PCA is a dimensionality reduction method, as we introduced, which compute the principal components while minimizing information loss. So what we will do, it's from the name, principal component. Principal component analysis means we will compute the principal components, and those are the orthogonal eigenvectors. So we will compute principal component 1, 2, 3, 4, etc. The ith principal component is a unit vector, okay, which is perpendicular to the first I-1 principal components. Meaning, if I compute principal component 2, it should be orthogonal to principal component 1. If I compute principal component 3, it should be orthogonal to principal component, 2 and 1, etc., etc. And orthogonal means what? Means what? It means this word, uncorrelated. There is no commonality between this new feature and the other feature. Orthogonal means this feature is uncorrelated with the other feature, because correlation means what? Redundancy. I don't want my features to be redundant, because what I want ultimately, I want the smallest, most useful features here, and that comes with what? With uncorrelated features, orthogonal eigenvalues, eigenvectors. Type. So let's see here. Typically these components, the number of components that I compute in my analysis should be less number of variables. Makes sense? Makes sense, because I don't want to increase number of variables. I want to reduce them. The principal components are orthogonal because we want data to be, my features, the computed feature to be uncorrelated. And the significance of the principal components decrease as the number increase. So, which means the most important principal component is the first one, then second one. What does importance mean here? It means how much information I have in the principal component, as we will see in the next example. Okay, so let's take an example here. And in this example, what I have, suppose we were giving the following samples of two variables. I have variable or features x and y, and I have samples here. Let's say, for example, these are students, and I'm giving you variables of what? Of, let's say, for example, x is the GPA of the students in their study, right? And y is their, let's say, for example, is their high school GPA. All right, anything. The x and y could be anything. Student 1, student 2, so these are samples. Or restaurants, the samples could be restaurants, and x and y can be, for example, x is the rating for the restaurants, and y is the cost to eat or dine in this restaurant. Or, for example, S1 and S2 and S3 and S4, these could be airlines. And X could be satisfaction reported by the customer, and Y is the price of the ticket for this. So you can see how this plays out in real life, okay? S1 and S2 and S3 can be candidates for an interview, where X is the experience, and Y is how many publications this candidate published in journals, for example. Okay, so now you get the idea. So I have here two variables, two features, two attributes, and here I have the samples. Okay, so suppose you are giving the following samples, x of two variables, x and y. Your task is to reduce these two variables to one variable. I want to reduce them to a one, حط لي خط, pay attention, to one new variable. ما حيكون لا x ولا y, it will be a new variable. Okay, to one variable, and report how much each variable explains the data. So we'll see how this is. So I can create a new variable and tell you I can explain the data by 90%. I have the information 90% for the data is just one variable. Okay, so now, okay, so the very first thing, what we will do, we're going to go through the PC algorithm in more of a graphical way to explain it. And then we go into algorithm, and then we go through numerical example. In fact, we have two numerical examples. All right, so the PCA here, let's say, first of all, let's plot this data. What data? Well, I have two features. What are these features? X and Y. This is a feature X or variable X and feature Y or variable Y. So question, what happens if I have 100 variables? And that's why in 100 variables we don't plot. We don't plot. We are plotting this example because we have two variables, and we are cooking up an example which is a very simple case, right? You don't plot if you have 100 variables. There is no meaning of plotting there. But we cooked up this example so that you have two variables so that we can visually understand how the PCA algorithm works. Okay, so the very first thing the PCA does as an algorithm, it says, I don't like really this data being scattered. What I'm going to do first, I'm going to compute the center of this data. How do you compute the center of data? Well, you average all the x coordinates for the data, because notice now my samples becomes points in this graph, right? My samples, which are these, now becomes an x and y coordinate. These are samples, becomes these values becomes an x and y coordinate. Okay, so I plot these samples, right, in this xy plane, and then I compute the center of the data. And then what? Well, and then I want to ship the data to the center. Okay, so why do I do this? Because when you shift the data to the center and you get rid of this DC value and mean value, it simplifies the analysis. It simplifies it when you deal with data when it is around the center. Right. Okay, then what? Then what we need to do? Then what we want to do is that we want to find the best line that fits the data. I keep trying with examples of lines here and there and there, and then I find, okay, this is the best line, which is this dotted black line. Well, how do I determine this is the best line? Well, I determine this because when I suggest a line here, which is the black line, notice that my data, the green dots, they start having projection in this line, which are measured by these blue dash lines here. Okay, these are the projections. And when I change this line, let's say, for example, if I may pick a pen here, if let's say, for example, I try another line here. Let's say I'm gonna try this line here. You will notice that these projection, the blue one, will be less and less, right? So my main target here, when I choose between let's say, for example, oh, where is my oh yeah, here we go. Okay, between, let's say, I'm gonna go back to my laser pointer here. Between this line here, which I just suggested, or this line, which is the black, I will choose the black because it maximizes those blue lines, right? I want to maximize them because I will have the longest projections. I call those scores. I want to maximize the scores because if I maximize the scores, it means this line represents better the data. Okay, so I keep trying these lines. Says, oh, this line here maximizes the length of these projections or the length of these. So blue lines. So here the best fit maximizes the blue distances and therefore captures the widest spread of the data. It minimizes the red distances, and red distance is how far these points away from my best fit. I want to minimize the red lines. I want to maximize the blue lines. Okay. The best fitting line is the black dashed line. Okay, and this now becomes my principal component one. So this dashed line now, my first principal component, right? And the blue distances here in the projections, the sum of these blue distances here, right? This one plus 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 this one are now the blue distances are the projections of, they are now referred to as the scores. So these are the scores now. Now the eigenvalue of this component is the total score or the total blue distance divided by n minus 1, where n here is number of points. In my example, n is 6 and n minus 1 becomes 5. So this is the eigenvalue. So what I am trying to do in the PC analysis is that I want to look for the best line which corresponds to the first principal component, which captures the breadth, the longest scores for this data, because it captures the most information about the data. That's basically the idea, what we are doing with PC analysis. And now, once I find the PC one, which is the first principal component, then I compute what is known as the eigenvalue, which is a unit vector. A unit vector means what? The length of it is 1. and it starts at the origin and it goes along the line. So this can be my eigenvalue, or in the other direction. It doesn't really matter whether either this way or this way. This I call it what? It is my eigenvalue. So V1 is the eigenvector, okay, and it's a unit vector, starts from the origin and points towards the direction of the line. V1 is a linear combination, okay, so it is a linear combination of what? Of x and y. What are x and y? Well, let's remind ourselves what are x and y. These are the features. So V1, which is my eigenvector, is a combination of the two features, which means نرجع لفلسفة ال PCA هلا, which means PCA creates the same feature, selects the same feature. No, it creates new ones, but new features which has more information about the older features. Okay. So this is V1, okay, and when you take the square of V1, meaning the distance, it equals to 1. And in this case, in our example, A and B are square root 1 over square root of 2, 1 over square root of 2. In this particular example, with this particular data, okay. Now I need to find out principal component 2. In fact, once you find principal component 1, principal component 2 becomes easy, because we need it to be perpendicular. Okay, and perpendicular, it's very easy to do that in the using the dot product. Okay, so this is V1, which is the eigenvalue corresponds to, the eigenvector corresponds to the principal component, first principal component, and this is V2, which is the second eigenvector, which corresponds to the second principal component. And principal component 1 and principal component 2 are my new features. Okay. Now, so if we use only PCA, so in my analysis, once I find the very first feature, I want to know how much information I am using or I'm retaining by using just the first principal component. So for example, let's suppose, for example, I use only PC1 for my data. I don't want to use PC2. So the question is how much information I retain, right? By just using PC1, how accurate my data is. Because the idea, I need to reduce number of features as much as I can. And this can be calculated by dividing the eigenvalue of the features that you are using by the total eigenvalue. So let's suppose, for example, I'm using only feature 1, okay? So how much information I retain by using feature 1, that is computed by dividing 20.2 divided by 20.2 plus 1.2, the total scores or the total eigenvalues. And that comes to be 94.4, which means if I only use PC1, I will retain 94.4 of the information of the data, which is quite excellent. Okay, I was able, by just reducing number of features from 2 to 1, I'm retaining 94.4 of the information. So now let's now we explain this in a graphical way. Let's go to the PCA in terms of an algorithm which goes steps, algorithmic steps, and we will see how we can get through these steps one step at a time, using equations, using mathematical methods, rather than doing things in a graphic way. But I introduce you to the graphical way so that you understand what happens under the hood, what happens with these equations, what are we trying to achieve here by this principal component analysis. So if we do the mathematical steps for the principal component analysis, we have to go through 4 steps. First of all, standardization. Second, covariance matrix computation. Third, eigenvector and eigenvalues, and fourth is the score and PC contributions. So let's go through this through the math. The very first step is the standardization. Okay, and typically what we do is that we have to compute the center of the data and then move the data to the center, which means subtract the center from the data. So every data we subtract the value minus the mean. Sometimes we divide by the standard deviation. This is an optional step. حقيقة, it is not all the time you see it. So let's go back to our example here. So here is my sample data. So what do? I have to compute the average for the x coordinate and the average for the y coordinate, and it turned out to be 5.5 and 2.5. Then what I do, I subtract these averages for the x and the y from all the points, and these are now my new points when they move to the center. So graphically what we have done, we move the data to the center by subtracting the averages from the points. Okay, so that's the first step, the standardization. Then what we need to do is that we need to compute a matrix which is called covariance matrix. The covariance matrix is a matrix where you have in the diagonal you have the variance of the variables, and in the other entries you have the covariance of the variables. So for example here, when I have a two variable, I will have the variance of x, the variance of y on the diagonal, and here the covariance of x and y and covariance of y and x. By the way, these are equal. Covariance of x and y is equal to this to covariance of y and x. If you have three variables, then notice at the diagonal here you have variance of x and variance of y and variance of z, and then covariance xy, covariance xz, covariance. You can imagine as if you have here x and y and z, right? And here as well, x and y and z. And whenever a variable matches itself, we use a variance. Whenever a variable meets another variable, we use covariance. Okay, so we compute the covariance matrix here, and then so how to compute these covariances? Well, the covariances of two variables, x and y, what we do is that we multiply the center data of these values. So this data already we did it, which is to subtract the averages. So we multiply the points and we add them and we divide by n minus 1. We'll see a numerical example for that. Okay, but really, what does a covariance mean in the logic way? A covariance is an indication of how the data is trending. So if you computed this covariance of x and y, right, and the value is positive, it means that both variables vary in the same direction. If whenever x increases, y increases. But if the covariance is negative, it means that the variables are not trending in the same direction. Like when one variable increases, the other variable decreases. And when your covariance is 0, it means, I'll leave it up to you. What do you think when you have a covariance of 0? What do you think happens? So just look it up and see and convince yourself what is the trending here. And obviously, the answer might be intuitive here as I explained it in these two lines. Now, what happened with the variance here, the variance of the variable? Well, the variance of the variable is the same as this equation, but now I use the variable twice. Instead of having x and y, I have just x and x. Okay, so I apply so the variance of the variable, it tells me how far these values are from its mean. So this is basically what it means, how I explain it. So now in the case of my example, okay. So in some of the textbooks or courses, you will see that when people compute covariance, they divide by n, and in some cases by n minus 1. So what's the deal here? Well, the deal here is that what are you looking at? Are you looking at the entire population? Let's say, for example, if I'm sampling 10 restaurants, and I have really 10 restaurants. In this case, you are really sampling the population, and you have to use n as 10. But let's say, for example, I am sampling 10 restaurants, and I really have 100. And in this case, you really need to use this equation, which is you are sampling few samples of the entire population. Okay, so it depends really what you are doing. But in our case, we'll assume that we are doing sampling, okay, of a subset of the population where we use n minus 1. Okay, so let's go to our example here. So what we did, we calculated the mean of the score, and now we need to calculate the variance of the variable. So these are now the samples after we moved them to the mean, right? Okay, or after we moved the mean of the data to the center, which means we took or we subtracted the mean from the points. Now I want to compute. Let's see if I have here a pen here. Let's see, now I want to compute the variance of x. So basically, I will here look at the values of these center data, which is this one here, right? And square it, and this one here, 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 and square it. Then after adding all of that, I divide by 6 minus 1. Number of points are 6, right? And I get this 10.7 for the variance of the variable. Similarly, I do the same thing for the variance of the y. And now if I want to compute the covariance of x and y, here's what I do. Let me change the color here. Okay, so what I do here is that I will multiply this point by this point, which is what I have here. Okay, and this point with this point, which what I have here, and this point, add the result by this point, which what I have here, and this point multiply by this point, which what I have here, and this point multiply by this point, which what I have here, and this point multiply by this point, which what I have here, and then divide by n minus 1, which is 6 minus 1, which is 5, and you get this number. Okay, and now I can create the covariance matrix, okay, by plugging in. This is the variance of x, variance of y, covariance of x and y, covariance of x and y. Okay, so that's now I got the covariance matrix. Let's go back now to the algorithm. What does the algorithm say? Well, the algorithm says now we need to compute the eigen values. The eigen values. So the eigen values are computed by solving this equation, the determinant of this matrix here. Okay, and we'll see in numerical example. And after that, we'll use this equation to compute the eigenvectors. So we need to compute eigenvalues, which, by the way, we use to compute the information retained by the principal component, and the eigenvectors, which are going to be used to compute the new projections of the data on the new principal components. So let's see a little bit of math here. So we need to compute the eigenvalues. We say that the determinant of this matrix here, okay, what matrix? It is this eigenvalue, which is here multiplied by the identity matrix minus covariance matrix. So this is the covariance matrix that we computed from the previous one, and these are the eigenvalue multiplied by the identity matrix. So we get this one minus this one, which is this matrix, to compute the determinant. You know that from math. Okay, so this is the determinant for this matrix. Okay, now I solve for this equation. So now obviously I have one variable here, and I get two solutions. The first eigenvalue, the second eigenvalue. Well, that looks very familiar, doesn't it? Right? If you go back to the example that we solve in a graphical way, right here. So we solved this example, and then we said Yeah, we computed these blue distances, which is the a projection of the first. Okay, this is, we computed this distance here. We added this to this to this to this to this to this. These distances, or we call them scores. When we added them, it turned out to be what? It turned out to be 20.2, which is, by the way, the first eigenvalue. And then when we added, well, let me go back to the graph. When we added these red lines, all right, these red lines, which is the the value for the second variable, when we added them, we got 1.2, which is the second eigenvalue. See, you see the connection between the graphical solution and the mathematical solution. So basically what we are doing in math is what we are doing in a graphical way. So we go back to our here, when we solve for eigenvalues, we got, let's see here, we got two values. We got this one, this eigenvalue 20.2, and this eigenvalue 1.2. Now, I don't need eigenvalues only, I need eigenvector. So from the previous side, we said you solve this equation. If you look here in the math, in the mathematical steps, we said that we solve for two equations. Am I going in front? Oh, yeah. So we use two equations. One equation for eigenvalues and another equation for eigenvectors. So I find the eigenvalues, done. Now I need eigenvectors. So I use this equation here. So come down here, okay, and let's apply this equation, matrix equation. So this one here minus the covariant matrix multiplied by V1, V2, right? And V1 and V2 are the components of the first eigenvector. Okay, so you can, so basically I need to do what now? I need to solve for these V1 and V2. Now, and this is V1 and V2 for the first eigenvector. And notice that I have two eigenvalues. One for 10.2, is that right? Am I getting this number correctly? Yeah, 20.2, sorry, 20.2. And the other one is 1.2. Now, to solve the eigenvector for the first eigenvalue, I plug the value here of 20.2 and then substitute for the numbers. You get two equations. ملخص equation, these are V1 equals V2. Well, V1 and V2, you will have many solutions. One of them, and since that I have a constraint that this vector has to equal to 1, this one possible solution, right? Another possible solution is to have both of them negative, minus 1 over square root of 2, minus 1 over, so you have multiple solutions. Now, the second eigenvector, which belongs to PC2, right, it should be perpendicular to this one. And perpendicular means the dot product equals 0. And this can be achieved by just making negative to one of the axes here. So this is here the eigenvector which belongs to PC1, right? And this one here is the eigenvector which belongs to PC2. Okay, now once we solve those, right, now I can say, all right, I need to compute the projections on the PC1 and PC2 of these numbers, which is, by the way, just for your information, when we looked at it in the graph, okay, basically the projections are the blue lines for computing the blue lines for PC1, and the red lines for PC2. These are projections, right? Because now I have really, this is PC1 and have PC2, and I compute the data projection here and there. Okay, the projection of data. Okay, let's see if I have a cleaner. Okay, so the projection of data. Let's take a look at this point. So now this is PC2. All right. So this is PC1. Right. If you look at this point here, take out this point here. Okay, so we make a projection here. This is the score of this point on PC1, right? And if I make a projection on PC2, this one here, the score and of the point on PC2. So this one, the score of the point on PC1, and this one, the score of the point in PC2. That's to compute those scores, okay, because they are important. What do I do now? I multiply my data. I multiply my data with the vectors. So here I multiply, so here I'm computing these scores. So for PC1, I multiply this data here, which is X and Y, which is, by the way, the center data, times the eigenvector, okay, which gives me this result. Okay, similarly for this point, which gives me this result, similar for this point, which gives me this result, similar for this point, which gives me this result, etc., etc. Okay, and similarly, then once I compute these scores on PC1, right, I do compute the scores for PC2, all right, and then PC1 and PC2, instead of using this eigenvector, I use the other eigenvector, which has a minus here, okay, and then I will compute these values, right? All right, I compute these values, and now basically, so what I have achieved here when I compute the scores of the points on PC1, basically now I can say that the points represented by just using PC1 are this. And notice how spread the points are. And that spreading is the information that PC1 holds about these points. That's why PC1 holds about 94%, because it spreads the points the most. Okay, so now I can say, all right, well, what's the contribution of PC1 to return the information? Divide its eigenvalue, which is 20.2, over the total eigenvalue, that's a 94%. And what's the contribution of PC2 to return the information in the data, which is 5.6. So now PC1 now retain most of the information, 94.4%, which is very high percentage. And that's because it is the axis that goes through through the data and represent them. So يلاحظ كيف البلج للداتا. This is where PC1 it comes in and represented. لاحظ أيضا إنه PC1 here has nothing, is not X and is not Y. It is not X and it is a new feature. It is a combination of the two. Okay, so خلينا نرجع لبداية الليكتشر, and I conclude in a minute or so. لبداية الليكتشر, my purpose here really, my purpose is to create a set of new features, right? Not the old features. طب why new features? Because I have two methods. في عندي feature selection, which is not what I'm doing, and then the feature projection, which is what I am doing. So the PCA creates a new uncorrelated features. That's what PCA does. All right. And in the next class, we will go through another example. We'll probably review the math steps again, and we'll see the other example, how now we can use this in an interview session. In an interview session, I have candidates, and these candidates have attributes, and we want to simplify this. Let's say, for example, I am accepting millions and millions of applications, and I'm collecting thousands and and thousands of features. I want to simplify this process. So what do? I use PCA. All right. Okay, I'm looking at the watch here. Thank you very much. I will stop the recording, and this should conclude the this session.